Okay, now here these characteristics are your common emitter configuration input characteristics. Here input characteristics are drawn between the input voltage VBE versus input current IB. Whenever the output voltage VCE is constant. Here input voltage VBE versus input current IB. Whenever this output voltage VCE is constant. Okay. Now here this common emitter configuration. The circuit is in active region. That means emitter junction forward bias, collector junction reverse bias. Okay, observe this waveform. This is similar to your PN junction diode forward bias characteristics. Now here, up to the cut-in voltage, there is no conduction. Because of that, when you increase the voltage, the current is 0. After reaching the cut-in voltage, the current is going to increase like this. Whenever the output voltage VCE is some 0 volts. Okay. And if you change this output voltage VCE to some other value, either 2 volts or 4 volts, then the characteristics are shifted towards right side. That means the output voltage is affecting this input characteristics. Because of that, the input graph is shifted towards right side. Okay. Now this, in this case, on x-axis we are taking this voltage VBE, on y-axis we are taking this current IB. Here IB is in terms of microamps. Here the base current is in terms of microamps. Why? Because in the case of emitter and collector, those two are highly doped material as well as moderately doped material. When compared to this emitter and collector, the basic doping level is very, very low. That means the current flowing to the base is very, very low. I discussed this topic in my first class of your concept. Here, the base current is very, very less when compared to the emitter and collector. So that's why we are going to take this IB in terms of microamps. You have to remember this point. IB is in terms of microamps, whereas IC, IE both are in terms of milliamps. Okay. This is about your input characteristics of your common emitter configuration. Now here output characteristics of your common emitter configuration. Now see, output characteristics are drawn between the output voltage VCE versus output current IC whenever the input current is constant. Now, if you observe this circuit, here output voltage is VCE, output current is IC. So you have to take output voltage VCE on x-axis and output current IC in terms of milliamps on y-axis. Whenever the input current IB is constant. Now here, input current IB is constant. Okay. Now here, to explain this graph, I am taking the equation of output current in terms of reverse saturation current. Okay. Here, I am drawing the graph between output voltage versus output current. So that's why I am taking the equation of output current in terms of reverse saturation current. Now this is the equation I discussed in previous class. That is output current is equal to the gain into input current plus 1 plus gain into reverse saturation current. Now IC is equal to beta into IB plus 1 plus beta into IC naught. Okay. Now here, if this reverse saturation current is not there, okay, here I am taking two conditions, that is without reverse saturation current and with reverse saturation current. How the graph is looking. Now first case, if there is no reverse saturation current, then what will happen? IC is equal to beta into IB. Then the equation will become IC is equal to beta into IB. Here IC output current, IB input current, whereas IC is equal to the reverse saturation current. Initially I am assuming this has 3 nodes. Now here what will happen? IC is equal to beta into IB. Okay. Now here this is input current now. In the case of output characteristics, IB is constant. Now taking IB is equal to 0. I am taking IB is equal to 0 and I am assuming this gain factor as 50. Then what will happen to IC and IC is equal to 50 into 0. It will become 0. IC is equal to 0 without this reverse saturation current. IC is equal to 0. Here IC is equal to 0. Now consider this reverse saturation current. Now consider this reverse saturation current. IC is equal to 0. The graph is here itself only, but because the current is 0. Okay. Here the current is 0. And after that what will happen? After that what will happen? Now this IC naught is increased because of the output voltage increases. Okay, why? Because the reverse saturation current is related to your output of common emitter configuration. See here, the output is connected forward bias and reverse bias. It is connected reverse bias. If you have to circuit, the output is connected reverse bias. That means the reverse saturation current is related to your output side. That means when you increase this VCE, otherwise when you increase the supply voltage on output side, when you increase the supply voltage on output side, because of the supply voltage, the output voltage across the transistor also going to increases. Because of that, IC naught is going to increases here. When you increase the supply voltage, at output side, because of that, the output voltage across the transistor VCE is going to increase. If VCE is going to increase, the reverse saturation current also going to increases here. Okay, when you consider this reverse saturation current, then after 0 milliamps here, now IC is going to increase from this 0 milliamps to the remaining value. Is it clear to everyone? Here, IC naught is increasing from 0 milliamps to the remaining value. This is whenever IB is equal to 0. Okay, this is the graph whenever IB is equal to 0. Okay, from 0 to remaining value it is increasing. If you observe here, this is 0 reverse without a reverse saturation current. Okay, and this is when you consider the reverse saturation current, it is going to increase. Similarly, when you take IB is equal to 20 microamps here, when you take IB is equal to 20 microamps, then what will happen to this equation? Without this, now here, without this reverse saturation current, IC is equal to beta into IB. That means IC is equal to beta, already we are assuming it as 50, and IB is equal to, we are assuming it as 20. Now 50 into 20, it will become 1000 microamps means it will become 1 milliamp. That means without this reverse saturation current, IC will become here. IC will become 1 milliamp. Why? Because IC is equal to beta into IB without this equation. That means without this reverse saturation current, IC is equal to beta into IB. It will become 50 into 20. 50 into 20 means 1000. 1000 microamps. Why? Because the IB is in terms of microamps now. 1000 microamps is equal to the 1 milliamp. Here, IC is equal to 1 milliamp without this reverse saturation current here. That means it is increased up to this value. That means we are not changing any output voltage. That means without apply this output voltage, we are getting this value is up to 1 milliamp like this. Up to 1 milliamp it is going to increase. Okay, and after that the remaining current is going to increase here. Now if you increase output voltage VCC, nothing but output supply voltage. If you increase the output supply voltage VCC, because of this VC is going to increase. Because of this reverse saturation current is going to increase like this here. When you increase supply voltage, because of that output voltage across the transistor is going to increase, and reverse saturation current also going to increase. That means when you consider this total equation, the output current IC is going to increase from 1 milliamp to the remaining value. It is going to increase here. IC current is going to increase from 1 milliamp to the remaining value. Now this is the increase of your output current. Okay. Similarly, if you consider 40 microamps, it will become 40 into 50, 2 milliamps. Okay, it is going to increase up to 2 milliamps. After that, remaining value is going to increase here. VCC increases, VCE increases, because of that IC not increases. Now the output current is increases from 2 milliamps to the remaining value. Like this, remaining also same. Okay. Now this is the output. Yeah, this is a common emitter configuration. Okay. Now in the case of common emitter configuration, what will happen to this input impedance, output impedance, current gain, voltage gain, power gain, and bandwidth? Here IZ is equal to nothing but input impedance. Here ZI, input impedance. Input impedance is given by input voltage to the input current. Okay, impedance is the ratio of voltage to current. So here it is input impedance. That means input voltage by input current. If you observe this circuit, this is the input voltage VBE, input current IB. So it is VBE by IB. Here VBE by IB. But here IB is in terms of microamps, very lesser value. That means this total value becomes high. Why? Because denominator is low, it will become high value. Okay. And after output impedance is given by output voltage VCE. output voltage is VCE by output current IC from this circuit. Output voltage by output current. This is a medium value. Okay. Similarly, if you observe the current gain is the ratio of output current to the input current. What is the gain? And the gain is dependent output quantity to the input quantity. But here it is current gain. So that's why the current gain is dependent output current to the input current, that is IC by IB. Here IC is in terms of microampere. Denominator is very low because of that current gain is high. So and after voltage gain is defined as output voltage VCE to the input voltage VBG. So here this is also high value. This is also high value. Okay. Here VCE is high, VB is low value. VB is low value. Because of this total value is going to increase. That means high. Okay. Now what will happen to the power gain? Already current gain is high, voltage gain is high. Because of these two values are high, then power gain is very, very high. And bandwidth also high. Okay, this is total about your common emitter configuration.